Let's move on to the x momentum equations. This becomes a little bit more involved. We have to go through each of the terms and decide which of them are important. So again, we're going to do the order of magnitude analysis on all of these. Let me just write this out where we can look at each term individually. So order of magnitude, right? Order of magnitude of all of these individually is going to tell us which of them are important. So starting on the left, what we want to do is come up with estimates for this. So starting on the left, let's say this one is rho times what's the change in velocity, that's u infinity, with respect to x, so that is rho u infinity over L. We also have another, sorry, what did I write there? Rho. Okay, sorry, this here is not a mu, that's a u. My bad. Okay, now I think I got it. So rho u du dx, so that's rho u infinity squared over L. So that's my order of magnitude of that first term. I think I got that. Okay, so that's fine, I guess. It's not helpful by itself. We can go through and do the other terms. So looking at the other ones, let's look at the second one here. So the second one is going to be rho times now v sub delta times u infinity over delta. Our v component of velocity is v sub delta, u component is u infinity, dy is delta. So the order of magnitude of that is shown there. That's, again, maybe not super helpful. So let's introduce to this the idea that v sub delta is approximately delta over L times u infinity. So plugging that in here, then we would get rho u infinity squared over L. I kind of wrote it sloppy, but taking this, plugging it in here for v sub delta, and that gives us this relationship. So okay, this tells us first term, second term, order of magnitude are the same. So far we can't throw anything away. Let's see, on the right-hand side, let's look at the minus dp dx. So here, what is the, let's say, what is the largest amount of pressure that could build by changing across the control volume? That would be let's say you have enough pressure where you could sort of completely stop the flow. So the order of magnitude of this dp dx term is the entire fluid momentum that's going through. So the entire fluid momentum is this. So the order of magnitude of this term over here is also rho u infinity squared over L. Okay, and then the remaining terms, let's see, we have the viscous terms. So the order of magnitude of this term is going to be mu times u infinity over delta. But it's the second derivative. So it turns out the approximate model for second derivative is to have mu u infinity over delta squared. That's the way of dealing with that. Okay, and then the last term here is mu u infinity over L squared, because that's in the x direction. All right, so what we can do to maybe compare all these terms is let's go through and divide by this momentum term here in all cases and see what we get out of that. So we go through and divide. We would get, just say, divide by rho u infinity squared over L. So then we get this first term becomes 1, second term becomes 1, third term becomes 1. The fourth term becomes something maybe a little bit interesting. So this is mu u infinity for delta squared times L over rho u infinity squared. That becomes L squared over delta squared, mu over rho u infinity L. And that becomes what? This over here is Reynolds number. So we have L squared over delta squared times 1 over the Reynolds number. Reynolds number with respect to characteristic length L. Okay. So this is a bit of a battle, right? We have something that's really big, L squared, or something that's really small, L squared. So this term is a really big number. This term is a really small number. So for most cases, it turns out that this actually goes to 1-ish, right? Order of magnitude. Really big number, really small number, order of magnitude is 1. All right, so that leaves the last term. So the last term dividing through, hopefully I have room here, would be mu times u infinity over L squared times L over rho u infinity squared. So this actually is just 1 over Reynolds number with respect to L. So that, we've assumed Reynolds number is big. So that has to be a small number. So for all of this work, we go through and we decide this term here goes away. Okay? But at least we know, right? At least we know that of all those terms, they have the potential to be about the same in terms of importance, but there's really no way that last term can be important. So that's the x momentum equation. What we're going to do is then do the same thing for y momentum, and we'll get a slightly different conclusion here. Okay, so for y momentum, I'm not going to bother rewriting it. You can sort of go through and rewrite distributing rho and mu throughout. But let's just do the order of magnitude for all of these terms individually. And what do we get? So first term is going to be rho u infinity v sub delta over L. Second term is rho v sub delta times v sub delta over delta. Let's see. Let's skip the pressure term for now. Let's do this second squared velocity with respect to y. That becomes mu times v sub delta over delta squared, right, for second derivative. And then the last term is mu times v sub delta over L squared. And let's keep in mind again that, just write it up here, v sub delta is equal to delta over L times u infinity. Okay, so what do we want to do here? I guess we can, let's see, delta. So I'm going to go through and I'm going to plug in any place where I see that v sub delta. I'm going to replace it with my approximation that of delta over L times u infinity. Okay, so if I do that, we get here it would be rho u infinity squared over L times delta over L. Here would be rho u infinity squared over L times delta over L. Skipping the pressure term for now, again, we'd get rho u infinity squared over L times delta over L. And last here would be rho u infinity squared over L delta over L times 1 over Reynolds number L, sub L. Okay, so starting, I guess, here. Rho u infinity over L times delta over L. So delta is very small compared to L. Reynolds number is very small, or very large as well. So this term for sure is going to go away. These other terms, I guess, these are all about the same order of magnitude. They're exactly the same order of magnitude. But we have to now think about this equation with respect to the x momentum equation. If we're looking at momentum that's going into a control volume or leaving a control volume, we could theoretically neglect one direction entirely. So this is saying there's no way that any of these terms in this equation are going to come close to the momentum in the x direction in a boundary layer, based on our approximations, right? We're always multiplying by this delta over L. So all of these terms that we've highlighted become unimportant, right? This one, this one, this one. Those are all trivially small compared to the x direction. Okay, but we haven't dealt with that dp dy yet. If everything in an equation is trivially small, and the equation still has to hold, what does that tell us about dp dy? It is also trivially small, right? It cannot be large, otherwise the equation would violate itself. It wouldn't be an equation. So we can, from this, just say that y momentum is negligible.